Have you ever just stopped and wondered what's really going on inside your phone or your computer? I mean, it all feels like magic, right? But deep down, at its very core, it's all based on a simple, kind of beautiful language. So today, we're going to pull back that curtain on digital logic, the secret language that, believe it or not, powers every single piece of modern tech. Okay, let's get into it.
So the big question right off the bat is, how do these machines actually think? Now, we're not talking about feelings or consciousness here. We're talking about how they process information, how they make millions, even billions of tiny logical decisions every single second. And the secret to how they pull it off? It's surprisingly simple. Yep, it all boils down to just this. The entire digital universe, everything you see, everything you do, is built on just two numbers, 0 and 1. This is what we call binary code, and it's the fundamental alphabet for every digital system. Every photo you take, every song you stream, it's all just a ridiculously long sequence of these two digits. Okay, but how do you actually represent an abstract idea like a 0 or a 1 in the physical world? Well, you do it with one of the most important inventions ever, the transistor. The best way to think about it is as a microscopic light switch. When that switch is on, it represents a 1. And when it's off, you guessed it, it's a 0. We're talking billions of these tiny little switches packed inside a single chip, forming the bedrock of all modern computation. It's incredible. Now, having a ton of switches is cool and all, but the real magic happens when you start combining them to make decisions. And that brings us to the next layer of this whole thing, logic gates. So what in the world is a logic gate? Well, think of it as a tiny little decision maker. It's a circuit that takes in one or more binary signals, our zeros and ones, and based on a very specific, unchangeable rule, it spits out a single binary output. It has no memory. Its decision is made instantly, based only on the inputs it sees at that exact moment. And here's the part that's going to blow your mind. Every single complex thing your computer does, from rendering a 3D video game to just sending a simple text message, is built from just three incredibly simple decisions. So let's meet the big three, the fundamental trio of logic, the NOT, AND, OR gates. First up, we've got the NOT gate. People also call it an inverter. This one is as simple as it gets. It has only one input, and its entire job in life is to flip it to the opposite. You feed it a 1, it spits out a 0. You feed it a 0, it spits out a 1. That's it. That's the whole job. Next, we have the AND gate. Now, this one's a lot stricter. It's the bouncer at the club. It looks at all of its inputs and will only, and I mean only, output a 1 if every single one of its inputs is also a 1. If even one input is a 0, the output is 0. It's totally an all or nothing situation. And this little chart here, this is called a truth table. It's basically a cheat sheet for how the gate behaves. And as you can see, it doesn't matter what the inputs are. If there's a 0 anywhere in the input, the output is always 0. The only way you're ever getting a 1 out of this thing is if input A and input B are both 1. You know, a really good way to think about this is like a high-security bank vault. To open that heavy door, to get a 1, you need two different keys, right? Key A and key B. And you have to turn them at the exact same time. If just one key is missing, that door is staying shut. No exceptions. And that brings us to our third basic gate, the OR gate. Now, this one is way more laid back than the AND gate. It will output a 1 if input A is a 1, or if input B is a 1, or if they both are. The only possible way to get a 0 from an OR gate is if all of its inputs are 0. And its truth table shows you just that. Look, the only time we see a 0 in the output is when both inputs are 0. In every other scenario, if there's a 1 on input A or input B, or both, the output is going to be a 1. Pretty straightforward, right? Okay, so we've got these basic gates, but how do we describe what they're doing on a bigger scale? How do we design and simplify circuits with thousands of them? Well, for that, we need a formal language, a set of rules for the game. We need Boolean algebra. And this isn't some new idea. Way back in 1854, a mathematician named George Boole came up with this whole system of logic. But for almost a century, it was just abstract math. The huge breakthrough came in 1938, when a brilliant engineer named Claude Shannon realized you could use Boole's algebra to design and simplify the very electronic switching circuits we're talking about. It's just a perfect example of pure math finding a home in practical engineering.
And just like the math you learned in school, Boolean algebra has its own order of operations. You always handle the not operations first, the inversions. Then you deal with the and operations, which you can think of kind of like multiplication. And finally, you handle the or operations, which are a lot like addition. Now, Boolean algebra is full of these clever little tricks, and one of the most famous is called De Morgan's theorem. You can think of it as a logic hack that gives engineers these amazing shortcuts. For example, it shows that an AND gate with its inputs flipped behaves exactly the same as an OR gate with its output flipped. And being able to make swaps like that is a huge deal. It lets engineers simplify really complex circuits using fewer parts, which makes everything cheaper and way more efficient to build. So we have our basic building blocks, not, and or. But what if I told you we could simplify things even more? Like, way more. What if you only needed one type of block to build everything? This leads us to the concept of universal gates, which is a total superpower. I want you to really think about that for a second. Could you actually design any digital circuit, no matter how complicated, using just a single type of logic gate? Just repeat it over and over and over again? It sounds impossible, doesn't it? Well, the answer is a massive, resounding yes. You absolutely can. And the secret lies with gates like this one, the NAND gate. All a NAND gate is an AND gate followed immediately by a NOT gate. But that simple combination gives it a very, very special property. That special property is called functional completeness, and it's what makes the NAND gate a universal gate. This is a gigantic deal for manufacturing. Imagine you're a Lego factory, but you only have to make one single type of brick. But from that one brick, you can build literally anything. That's what universal gates like NAND and NOR do for chip design. You can mass produce one simple component, which drives costs and complexity down like you wouldn't believe. Okay, wow. So we've gone from the basic idea of binary through the decision-making of logic gates to the math that governs them. Now, let's tie it all together and bring it back to the physical world. Let's go from the idea to the reality. Right, so here's the most crucial connection to make. On a diagram, a logic gate, like an AND gate, it's just a symbol. It represents a rule. But inside a computer chip, it is a real physical thing. It's a very specific arrangement of those tiny transistor switches we talked about at the very beginning. The abstract concept becomes a real working circuit. And this table gives you a little peek at how it's done. Engineers use different types of transistors that basically behave in opposite ways. One type might turn on when you give it a high voltage, while another type turns off with that same high voltage. By combining these opposite behaviors in really clever ways, they can physically build the circuits that behave exactly like the AND, OR, and NOT gates we've been describing. So, in the end, what's the big takeaway? You know, I think this quote sums it up perfectly. A complex digital system is like an orchestra. Each individual logic gate is just one musician playing one simple part. And Boolean algebra? That's the musical score. It's the masterpiece of logic that tells every single musician exactly when to play and what note to hit, making sure all those signals combine to create the beautiful, complex symphony we call computation.